So this is what I asked you to copy down last time. Basically, the nucleophilic substitution of your halogenoalkanes. There are two types. Everyone is lazy, and you're right. SN1 and SN2. Sorry. SN1, as I said, the number 1 stands for it being a unimolecular. There's only one species that is in charge in your slow rate determining step. Okay, the S stands for substitution, the N stands for nucleophilic. So the way to memorize this is that in your first slow step, there's only the halogenoalkane involved. Okay, so as you can see, the nucleophilic, the nucleophile is not attacking in the first step, right? This is the slow step. That means there's only one molecule that is present in the rate determining step. So what happens if you don't have a nucleophile to attack? That means the only possible thing to happen is the breaking of that carbon-bromine bond. Otherwise, you can also memorize it as tertiary halogenoalkanes tend to go via the SN1. Okay, so this reaction goes through a two-step process or two-stage process. Okay, one is the slow process and the other one is the fast process. Okay, so that's just what I have talked about. The second one, SN2, again, it's a nucleophilic N substitution S. 2 means there are two molecules or two species, sorry, not molecules, two species that appears in the slow rate determining step. Okay, so if you look at this, you have the halogenoalkane, that's one species, and then you also have the hydroxide ion, that's the other species. Okay, both of them appears in your rate equation, right? And both of them, since the quantity is only one, that's why the order is 1 respectively. Okay, halogenoalkane raised to the power of 1, hydroxide ion, which is your nucleophile, raised to the power of 1. Right. The next learning objective is moving away from rate equation, moving away from mechanism. We are going to look at the different techniques for studying the rate of reaction. Okay, how do you study the rate of reaction? It all depends on the equation. Okay, right. So we need to select a suitable method to follow the progress of a reaction. It can either be the disappearance of your reactant or the appearance of a product. Okay, there are two types of methods. The first one is continuous method. That means you monitor from the start till the end. Okay, sampling method. I think some of you are familiar with this term. Sampling method means you take small samples from the ongoing reaction. Okay, the easiest one is the continuous method, so I'm going to go through that first. The first one is monitoring reaction rate using mass loss. Okay, so this is when we have a disappearing of reactants. Okay, usually this involves a reaction that has that produces gas. Okay, and if you let the gas escape, that means the mass will decrease. Right, so basically you just put your reaction mixture in a weighing balance and then you monitor the weight loss. Okay, at the start of the reaction, and then over time your mass should decrease because you are losing the gas molecules. You let the gas molecules escape. Okay, so this is an example. If you have metals reacting with acids, okay, metals reacting with acid, an example that they have here is zinc with hydrochloric acid. You're producing salt and hydrogen gas. The salt will stay in the reaction beaker, okay, or conical or flask, whilst you let the hydrogen gas escape. So obviously, if you let things escape from your reaction mixture, your mass will decrease. Okay, this is generally for reactions that produces gaseous products. Sometimes one reaction, there are several methods that you can use. Okay, so there's no strictly one method, but the method that you have chosen must make sense, right? Let's see, what do you have in your notes? Okay, so please copy this down where it says generally for reactions that produce gaseous products, you will use this rate loss method. Sorry, mass loss method. Okay. Ang, are you copying this down? Ang is not replying. I don't even know if he's listening. Yes, okay. That's a good test. I should just pick one person randomly and then ask him or her whether he or she is listening. Isa, are you copying this down? Nick is not in here. Good. Okay, done. Right, the next one is monitoring reaction rate using volume of gas. So again, obviously this is quite obvious. If your reaction produces a gas product, you can also monitor the rate by collecting the gas, okay? Whether you collect the gas using the gas syringe or using the water displacement, okay? You've done that in your practical, okay? So changes in gas volume or gas pressure can be measured. So you just record the increase in volume in the syringe or measuring cylinder if you're using the water displacement. You record the volume of gas that you produce over time. So from here you can find the rate, okay? This is an example of a reaction of a carbonate with acid where you form salt, water, and carbon dioxide. Okay, this also works with reaction of metal with acid. Okay, the gas may be collected in a gas syringe or an inverted water filled with burette or filled with a measuring cylinder. This is again generally for reactions that produce gaseous products. Okay, that's quite straightforward as well, right? Next one is when you have small changes in volume, okay? In the previous method, mass loss and measuring the volume of gas produced, this is for when there is a big change in volume, okay? The progress of some reactions can be followed by measuring small changes in the volume of reaction. So we use a dilatometer, okay? It is used to measure small changes in volume, and the temperature of the reaction has to be controlled. Now you cannot, you have to ensure that temperature is constant. Why? Why do you think? Basically, this dilatometer reaction is happening, but when there is increase in pressure, it will push the oh, sorry. No, this has nothing to do with pressure. So looking at this example, which is the hydration of this alkene, okay? So what happens is that the alkene will take up the water to form alcohol. Okay, so when they take up water, it's not something that we can measure because it's very little amount of water. So you can see that this bulb, okay, when the alkene has taken up water, it will increase. Okay, it will increase in volume, and then you can read it from the scale. And it's in a capillary tube. A capillary tube is a very narrow tube, so that any small changes, you can see that the liquid is moving significantly. Okay, now to answer my own question that no one answered just now, the reason why we have to keep the temperature constant is because if you start increasing the temperature, the liquid will expand, and so that will change the reading. Okay, and we don't want that, because we want to know how much the volume changed based on the reaction only, not from the change in temperature. Right, next is monitoring reaction rate using the formation of precipitate. This is also a reaction that you have done in your practical. So you measure the time taken for a small fixed amount of precipitate to form. Basically have an insert at the bottom of your flask or beaker. It can be a writing, it can be a cross or whatever. And then you add your reactants, sodium thiosulfate and sulfuric acid, and then you will record the time for the sulfur precipitate to form. Okay, when do you stop? When when the bottom of your beaker is completely covering the writing on the paper. Right. This is generally for reactions that produce precipitate starting with clear solution. You have to start with a clear solution, and then you end when you have produced precipitate. Okay, so that's, again, nothing difficult. The reaction is given on your notes. Sodium thiosulfate reacts with hydrochloric acid or sulfuric acid to form sodium chloride. Is fine. It's just an aqueous solution. Water is also colorless. Sulfur is the precipitate that you are observing. Okay, sulfur dioxide is the gas. Next one is monitoring reaction using changes in electrical conductivity. You do not, you have not done this. Basically, you use a meter, okay, pH meter. This is used for these reactions. I hope that's quite obvious that the reason why we measure the electrical conductivity is because you have ions. Okay, so this method is generally for reactions that contain ions. If you don't have ions in your reaction, then there's no use of using the pH meter to measure the electrical conductivity. Okay, the reason why pH meter works is because you have the hydrogen ions. So either hydrogen ions or hydroxide ions. You can use a pH meter for this. The next one is also something that you probably have not done it. I'm not sure if you have done it in bio. It's called the colorimetry. This has something to do with the intensity of the color. Okay, so you can use a colorimeter to monitor the progress of your reaction, but the idea is that your starting color and your final color in the product must be different. Okay, okay, so generally for reactions with different colored reactants or products. So in this case, we have a ketone and iodine to form this product, and a hydrogen iodide. Okay, now iodine is the colored one in this case, right? Depending on the concentration of your iodine. What happens is that if we were to monitor the color using our naked eye, it's fine, but we won't be able to do it accurately. Okay, we're only able to say, oh, this color started from a very dark, say dark brown or dark purple, and then as it progresses, it becomes lighter and lighter. Okay, so we can only talk about the color qualitatively, but a colorimeter can quantify. Okay, this one is dark, so the concentration is really high. They can even calculate the concentration for you. And then over time, when the color of iodine decolorizes or getting lighter and lighter, which is hydrogen iodide. Hydrogen iodide is colorless. Okay? The colorimeter can tell you the concentration, right? Here, what I have on this diagram is just showing you how a colorimeter looks like inside the machine. But again, you don't have to worry about that. Okay. So that was the continuous method. Basically, you let the reaction run until it finishes. Sampling method, usually this is done for titration, okay? Sampling method involves taking small samples of the reaction mixture at various times and then carrying out a chemical analysis on each sample, okay? So this is an example of a reaction that I can use sampling method to monitor it. I will put them in a beaker, okay? My haloalkanes and my sodium hydroxide in a beaker, and then depending on the question, the instruction, or depending on yourself, if you want to take reading at intervals of say maybe 2 minutes, okay, every 2 minutes you will take out a small fixed amount or fixed volume from your reaction mixture, okay, say remove 10 centimeter cube every 2 seconds, okay. So I will take the first 2 minutes, okay, I will take 10 centimeter cube of my sample, and then I will stop the reaction in the sample only, okay? But the reaction in my beaker is still continuing. It's still continuous, sorry, right? So this stopping is called quenching, right? So small amounts of the reaction mixture are withdrawn by pipette at regular intervals, and the concentration of either product is determined by titration, okay? So when I withdraw 10 centimeter cube during the second minute, I have to stop it because that is the sample for second minute. If I don't stop the reaction, okay, in my sample, only in my sample, that means the reaction is continuous, okay? So we have to quench. There are a few ways of quenching or stopping a reaction. One of them is cooling by adding ice. Okay, when you add ice to your sample, the reaction stops. So now you already have a sample at 2 minutes. Later on at 4 minutes, you need to take out 10 centimeter cube again from your reaction mixture. Okay, you take out 10 centimeter cube, and this is the sample at 4 minutes. Again, you have to stop that reaction. You only stop the reaction inside your sample, not in your reaction mixture. Okay, so again, you quench it, and then eventually, right, after you have a few samples, in order to find out the concentration in your particular sample at 2 minutes, sample at 4 minutes, sample at 6 minutes, 8 minutes, you will carry out a titration. Okay, so that's the only way to pause time, to pause the reaction whilst your reaction mixture is still going on. Okay, so the concentration of hydroxide can be found by titration with a standard solution of a strong acid, right? Is that clear? I hope that's clear, the difference between sampling method and continuous method. Okay, so this is generally for reactions that contain hydrogen ions or hydroxide ions on one side, or any ions that are suitable to be carried out in a titration method. Okay, please copy that down. Are you done? Okay, right. So that's all. That's all the methods. Those are the list of methods you can choose from to monitor reaction. Okay, this is mostly important for your paper 5. They will give you a problem and then they will say design your experiment to monitor or to calculate the rate of reaction or to calculate the rate constant. So you have to be smart in choosing which method works for that particular example. Okay, next one is enzymes. Okay, so there are two types of enzymes. The first one is heterogeneous, and the second one is homogeneous. Hetero means the catalyst is in a different phase to the reactants. Homo means same. Okay, catalysts and reactants are in the same phase. So what do we mean by phase? Phase and state is not the same. Okay, phase is when a boundary exists between two components. So for example, you can have two liquids, say oil and water. They are in the same state, liquid state, but they are in different phase. Why? Because they don't mix. There's a boundary. So whenever there's a boundary between two species, then we say that they are different phases. Okay, like two immiscible liquids are in two different phases. We'll look at the heterogeneous catalysis first. Okay, heterogeneous catalysis often involves gaseous molecules reacting at the surface of a solid catalyst. Okay, so heterogeneous catalyst usually involves catalysts that are in solid state. Right? If you look at the learning objective, like your Haber process, the production of ammonia, where you have nitrogen gas reacting with hydrogen gas in the presence of iron. Okay, iron is a solid. So there are 5 steps in this heterogeneous catalysis. The first one is diffusion. So if you look at this diagram, your reactants, okay, this is an example of Haber process, okay, your reactants, hydrogen molecule and nitrogen molecule, will diffuse on the surface of your catalyst. In this case, it's the ion, okay. The second step is adsorption. Please be careful with the spelling and do not confuse it with absorption, okay. Adsorb means it sticks onto the surface of the catalyst, okay. Absorb means it goes through. I hope you know the difference, right? So how is this adsorption happening? You know, you don't just get reactants molecule sticking to the catalyst just because they are catalysts and reactants. Actually, you have a weak intermolecular forces. Okay, so there is a weak intermolecular forces between the solid catalyst and your reactant molecules. Okay, the criteria, your intermolecular forces must be weak enough so that the products can leave. Okay, so it's weak enough to break and release the products from the surface of the catalyst. It must be strong enough to weaken the covalent bonds. Okay, so this is what I mean. When we have hydrogen molecule and nitrogen molecule to stick to the surface of the ion, it must be strong enough to hold them, okay, while the hydrogen molecule is sticking onto the ion. At the same time, the hydrogen bond here, the single bond, is being weakened, is being broken, okay? Same thing as the nitrogen molecule sticks onto the surface of the ion catalyst, the triple bond is being weakened or broken, okay? So that needs to be strong enough to weaken the covalent bonds, okay? But don't worry about that. Next one is the reaction. So after the breaking of the bonds, you have atoms, okay? You see this hydrogen atoms, the hydrogen bond is already broken. You have nitrogen atoms, the nitrogen triple bond is already broken. Instead, they form a bond with the catalyst, okay? But this bond must not be a strong bond, because if it's a strong bond, then it's difficult to break it later for to release the products. Reaction, so this is where the reaction is happening. The nitrogen atoms and the hydrogen atoms combine together, okay? They form new bonds whilst they are attached onto the surface of the ion. Next, once your product is formed, you see here ammonia and H3 is already formed, then it's time for desorption. Desorption is the opposite of adsorption, okay? They unstick, right? The bonds between the ammonia product and the surface of the ion catalyst will be weakened and are eventually broken, okay? So then the last one is diffusion, where your product, ammonia product is being released and it diffuses away from your catalyst. Okay, right. Okay, right, the steps, not so bad. You have to memorize the steps if they ask you to explain heterogeneous catalysis. Okay, another example of heterogeneous catalysis is the catalytic removal of your nitrogen oxides in car exhausts. Okay, so what catalytic converters do inside your car exhaust is that it converts all your harmful gases into a harmless one. Okay, so this is your nitrogen oxide and carbon monoxide, right? The catalyst that they use in the exhaust of your car would be your transition metals, okay? Platinum, palladium, and RH, I think it's, can anyone remind me what RH is? Is it rhenium? Please look it up. Rhodium, is it rhodium? Please look it up, okay? Because I always forget what RH is, but it is a transition metal, okay? These are the rhodium, okay? Right? Two people have said that it's rhodium, RH. Up to you if you want to believe your friends or if you want to look it up yourself, okay? So these are considered as one expensive metals, okay? These metals are deposited as thin layers into a ceramic honeycomb structure. The reason for this honeycomb structure is to increase the surface area, okay? So this is the reaction where you have carbon monoxide and nitrogen monoxide. It goes into the catalytic converter that contains either platinum, palladium, and RH, okay? And then you transform your carbon monoxide to a carbon dioxide. Now, it's not to say that carbon dioxide is not harmful. It is a greenhouse gas, okay? But it's less harmful than carbon monoxide, right? Your nitrogen oxide will be converted to nitrogen gas, which is definitely not harmful nitrogen gas, right? This is how it looks like. If I don't know, I've not seen an exhaust car, but this is the honeycomb structure that I was talking about, okay? The honeycomb structure, this is where you have deposits of your transition metal. So that's where your carbon monoxide gas will adsorb themselves and nitrogen oxides will adsorb themselves onto the surface of the catalyst. Okay, the steps. The first one, well, if you remember previously, it would be the diffusion, okay? Your carbon monoxide and nitrogen monoxide will diffuse onto the surface of the catalyst, whether it's palladium, platinum, or RH, okay? And then it adsorbs onto it, okay? Adsorption of nitrogen oxide NO and carbon monoxide CO onto the catalyst surface. I think that's empty on your notes. Yep. Can you please copy that down? We have about 8 minutes left. Okay, next one is reaction. This is where the reaction is happening. So you first break the bonds between the carbon and the oxygen so that you have carbon atoms and oxygen atom. And you also break the bond of the between the nitrogen and the oxygen so that you will have nitrogen atoms and oxygen atoms. And during this process is also where you form new bonds. Okay, formation of new bonds between the adjacent nitrogen atoms to form N2 molecules, which is your product, and the CO molecule and oxygen atom to form CO2. Okay. Some of your CO molecule that was not broken will combine with the oxygen atom that was broken from the CO, right? And then the next one is desorption. Okay, while you're copying this down, desorption is just releasing of your products, your nitrogen and your carbon dioxide products, right? While you're copying, I'm just going to move on with catalyst poisoning, okay? Catalytic converters can be affected by catalyst poisoning. As you know, catalysts, just like enzyme, they can be denatured, but because catalyst is, we say it's an inorganic enzyme, we don't call it denaturing, we call it poisoning, okay? Once your catalyst is poisoned, then you can't use it anymore, right? Happens when substances not involved in the reaction is strongly adsorbed onto the surface of the catalyst, preventing reaction. So I think this is the same idea as inhibitors, I think, because inhibitors goes into the active site of an enzyme, okay? But here, we don't call it inhibitors, we just say that reactants that are not supposed to be involved or species that are not supposed to be involved in the reaction, they start adsorbing that themselves onto the catalyst strongly, okay? And so this just poisons the catalyst. You can't use the catalyst anymore because you have an unwanted product sticking onto your catalyst very strongly, okay? A common catalyst poison for catalytic converters is lead, okay? So lead will bind or adsorb itself strongly onto the catalyst until the catalyst cannot be used for their main reaction, okay? Next one, copy down for desorption of nitrogen molecules and CO2 molecules. Okay, I actually wanted to finish off this whole thing, but I don't think I would rush through it. The next one is the homogeneous catalysis. Again, it's nothing, it doesn't require a lot of explanation. All you have to do is just read it. They're all basically description. And the next section, the very last section would be enzymes. Okay, so I want you to read them at home. And then I will just go through it briefly. Most of them involves equations that you just have to memorize, okay? Some, perhaps this iodine persulfate reaction, I would just go through it briefly and explain that double hump, right? But for enzymes, I think should be quite obvious, okay? So maybe in 15 or 20 minutes, I should be able to finish this topic, okay? So after this, we will do some exercise, some questions first before we start on to the next topic, okay? Next topic is organic chemistry, and I'm still thinking about that. I'm still planning how I'm going to teach you because it requires drawing, and I do not have an access to like a drawing pad or an iPad. Right. Everyone, are you okay? Do you have any questions? Do you need to go back to any of the slides? No? Wow, everyone's so quiet today. I'm literally talking to myself. I've already unmuted you. Kai Xiang, are you there? Hello, Kai Xiang. Yes, he doesn't want to say anything. So no questions?
No.
Everyone happy?
No.
Yes.
Iqbal, no question? Okay, so